All right, so let's help me out here with what did you have for the original plan on day 5? Day 6? Day 7? Day 9 or day 8? And day 9? 512. Just started out with that one little dollar, and now already at day 9 we are up to $512. How about the new improved plan? Man, we were getting more money with that. What is it on day 5? 45. And how about day 6? And day 7, and 8, and day 9. And suddenly, we're like, oh. Now, so if we were just, I think then below now, it gives us some options to talk about this. We have already said that the original plan is exponential. It's exponential growth. We are doubling, just keeps multiplying times 2. The new plan is linear. So this one was exponential and linear. And so for the original plan, I could say y equals, the starting amount is just $1, and then it's times 2, and then our exponent is how many times we're timesing it by 2. So it's like the 100% plus another 100% to make it times 2. And the new plan, it's changing by $5 every day. That change is the slope, and it's starting out at 20, so plus 20. So we've already completed the table, so we don't need to worry about completing the table using the equations. We could check a few spots in the equation to make sure that it's right. So like if I want to know, like we just followed the pattern, I think. So what if I thought, well, I want to know if I did the right thing. So if I did y equals 1 times 2x, and I made x and 8, so 2 to the 8th power, does that, and remember, 1 times anything, I really could get rid of the 1. I could just say 2 to the 8th. So what is 2 to the 8th? Does it agree with what we have in our table? Yes, good. Because if we did use our formulas, so if we were comparing the two plans for days 1 through 5, what could we say if we're comparing for days 1 through 5?
The new improved plan gives you more money.
Okay.
For those days.
Yes, for those days. Yeah, the new improved plan is more. It seems better. It seems improved, right? So it's better in the short run, just for those days. And then what do we already see when we get just 6 to 9? How are 6 to 9? Is the new improved plan still more? Absolutely.
The original plan gives you impressively more money.
Yes. The original plan gives, as Chris said, impressively more. You don't necessarily have to use the word impressively, but it is not just a little, right? So if this were to be carried out for 30 days or longer periods, so the longer the time frame, the more the exponential way is going to result in extremely more money, right? So beyond a few time periods, the exponential model is going to grow much faster. So initially, we might not see too much. You see on the next page that there is a graph, and we see that the initial growth looks really slow and then zoom, right? So between 5 and 6 days, it's right there, we see it cross, and then there's the big switch happens. And then continues in that manner so that the amount is still growing the other way, but it is not changing nearly as fast as the exponential. So now we're going to look at interest, and we're going to look at interest as simple interest. And then after simple interest, we're going to see compound interest, which is really how the world and the financial system works.
Sorry. Said this is literally business math.
Yes, there's a lot of business math in there. Yes. Yep. So if I was going to do just simple interest, it would just be the principal times the rate times the time. So if the interest is 4% and it's just 1 year, then $40 a year. At the end of the year, it would be $1,040. Now, this is simple interest, so you're not getting interest on interest. So if we wanted to know for 3 years, we would just triple that. So we would just do 40 times 3. So I could just do 40 times 3 because the time would have been a 3 instead of a 1. So that would be $120. And then the ending balance, well, they still got their $1,000 they put in. Please don't just say 120. That would be a sad thing. So $1,120. So the same amount would be getting added each year. And so even though it's interest, this would still be a linear function because it's just adding on the same $40 every single year. So oftentimes, like simple interest, like among friends or just on a really short-term loan, you might see simple interest. But it is more realistic and more often used is actually compound interest, where you either earn or pay interest on interest. Now, it can be compounded annually. It can be compounded more often than that. So first, we're just going to look at annual because it's the simplest, and then we'll break into. So if the initial deposit is earning $1,000, or is $1,000, and it's still 4%, but now it's compounding interest. Well, if it's compounding, that means the interest gets added on. So notice what happened here. You could stop, figure the amount, add it on, stop, figure the amount, add it on, but it would become exponential now. So remember our growth rate and our growth factor, that like 104%, that's what's happening inside there. And then the number of years is your exponent. And then this is money, so we're going to round to the nearest cent. So this would be $1,124.86. So you might test that, make sure that's what you get if you put it in your calculator. By the way, you could put it in the calculator just like that, or you could do 1,000 times 1.04 to the power. Now, they're going to get to be somewhere it's maybe handy to leave it because it gets really messy. But right now, we can very easily add that. And then if I want to know the total interest, how much of that is interest, I take away the principal. Whether this is money that I am investing or I have to pay, I still take away the principal, and what's left must all be interest. So at that point, 124.86. All right, so try that for 4. What do you get for the 4th year? What's our total after 4 years? Notice the formula here gives us the total amount, and then we have to subtract to get how much of it was interest. So for year 4,
1,169.86.
good. And then we can do the subtract 1,000 pretty easily. 169.86 would be the accumulated amount of interest. And if I wanted to know the interest just for year 4, I'd have to do the subtraction between year 4 and year 3. The 169 is all the interest that they've gotten the whole time. And now we break 1,200, $1,216.65. So 216.65 cents. So the interest earned in the first year is still just the $40. How much interest was earned in the second year? So we'd have to take that 81.60 and subtract the 40 to get 41.60. So if I want it, so the accumulated interest is all the interest so far. So if I wanted to know for just 1 year, I would subtract it with the year before. So in this case, how much interest was earned during the 5th year? So during the 5th year would mean we need to take year 5 and subtract year 4. Anyone else? 46.79. So everyone get what I subtracted there? If I want to know how much of it was earned in year 5, I take the accumulated amount for year 5 and subtract. It's just an absolute change from the year before. And then if I wanted to know, we got a second question, how much more is this than the first year? Well, the first year was only $40. So I'd be taking this, subtract 40, so $6.79 more than the first year. That is the power of compounding. Right, so on our next page, again, this is still just compounded annually, so things aren't getting much trickier. Remember that you're going to change the percent to a decimal and add it to 1 to make your growth factor. The initial deposit or the amount you borrow is always that initial amount that's on the outside, very similar to what we did last week. Times, or you could use parentheses, 1.0225. So it's getting long there. And then that is raised to the 5th power. And again, you can put that all in your calculator at once, but whatever you do, please do not do 2,000 times the number and hit equal and then raise it to the 5th power, because that would give you, well, it should be a number that would be so ridiculous. Well, it would go in scientific notation first off, but should not seem reasonable. So 2,000, how much? And 36 cents. Good. And so how much interest accumulates after 5 years? What's our total interest after the 5 years? Right, we're just going to subtract the 2,000 because that's the money we started with. So the other money that's in the account would all be interest. So to find how much will be in the account after 10 years, use our same formula, just change your exponent to a 10. And then see what your comparison to think about after you find out the interest, and then answer E. And then we're going to compare to how much the interest would be with just simple interest. Hello? Hopefully everyone came out with $498.41 as the amount of interest that accumulates after 10 years. Is that exactly, is it double the amount that it was at 5 years? Is it more than double or less than double? More than double. Okay. Okay. So if we were doing simple interest, it would be exactly double. So it's more than double. And if we were doing simple interest, and all we were doing, remember, simple interest is principal times the rate times 10 years. So if we did it with simple interest, we would only earn $450 for 10 years. So we can see that even if we're only compounding annually, that ended up being close to, well, more than 10% difference if we do the 10% of the 45. All right, so pretty big difference, especially if you consider like thousands, millions of dollars. So that was just compounded annually. At the end of every year, the interest would be figured, added into the account. The next year, you would get interest on the original amount plus interest on the interest. But our formula takes care of that, so we don't have to use like 1,000 different calculations. What we're going to look at next is, again, what is even more common is that things are often not compounded annually. They could be compounded quarterly, which is 4 times a year, monthly, or even daily. So the concept is the same, except now if it's compounded, say, monthly, then each time they figure the interest, you're only given 1/12 of the interest, but you get it more times. So there's a trade-off here. In this example, this is quarterly. So since it's quarterly, it's 11% is the annual rate. So the quarterly interest rate is just the 2.75% or 0.0275. That number came from dividing this. That's where this comes from. The trade-off is I divide the interest rate by 4, but then instead of just 3 years, there are 12 compounding periods. So we divide this number by the 4, we multiply that number by the 4, if it's quarterly. So each time the interest is figured, it's a smaller percentage, but then it's added on and the compounding is happening more frequently. So if I have in this next example, and you could put that in your calculator just like that looks. If this division doesn't come out to be nice and neat, it doesn't end, then I would encourage you to put it in the calculator like that so that you keep all the accuracy possible. Obviously, 4 times 3 we can easily do in our head to get 12. So here, if this is 6%, we're still working with that same exponential growth formula. So 2,000 is our initial amount. This is compounded quarterly. There are 4 quarters in a year. So I'm doing 1 plus 0.06 divided by 4, and then it's 8 years, but the 8 gets multiplied by 4 because there would be 32 quarters. Now, 0.06 divides pretty easily. So like what I actually wrote down on my paper was 2,000 times 1.015, because that would be 1.5% each quarter, and then 32. And then we have some other, then of course we're going to put that in the calculator, but if it's compounded monthly, so there are 12 months in a year. So if it's compounded monthly, if I do 6% divided by 12, then each month they are only getting 0.5%. Now, again, you can put that in the calculator like that. I would go ahead and at least do this part. Or you'd have to put it in parentheses. If you're putting it in the calculator, it would have to be in parentheses. But 6, this does come out nicely. It's just 1.005. That's what 0.5% looks like. And then this, now the trade-off though is it's to the 96th power, because there would be 96 interest-bearing periods, 12 each year. And then compound it daily. Daily is not going to divide nicely. So daily, I would put this in my calculator. 0.06 divided by 365. I use the slash. And then up here, you could do 8 times 365, or you could figure out that number in advance. If you don't figure out the 8 times 365 in advance, you do need parentheses after your exponent. All right, so take a minute, go ahead and figure out how much each of these would be, and then answer part D. All right, what did someone get for A?
For A, I got 3,220.65 cents.
Me too. Good. And B? Me too. So far, so good. And how about for daily?
I got 30,232.02
And 2 cents. Same. So what we see, and what I already gave you the hint as you were working it out, is that more frequent compounding yields a higher interest. Of course, a higher percent makes sense that it would make a higher interest. But if you had the choice, if you're getting the interest, if you are investing, you would want it to be compounded more frequently, because it's going to make the interest, the actual interest, might not a huge amount, but this is $2,000. What if it was $20,000? Then 10 times as much. And if it was $200,000, a retirement account or something. So that difference between the 20 and the 32, add some zeros, so $12, but add some zeros on that. And then in contrast, if you were borrowing, then you would hope you're not hearing that your interest is compounded daily, because that means that it's going to be even more. And of course, we could have compared that to just compounded annually, which would have been even smaller. We would have gotten an even smaller number. Speaking of borrowing, let's look at number 3. It is a borrowing question. So you borrow $10,000, just to kind of point out that these things could be used if you're borrowing or if you have an investment. It's a matter of if it's in your favor or someone else's. It's compounded weekly. So how many weeks in a year? 52. 52. So, and this is a real kind of semi-real life thing here. When you borrow money for tuition, like a student loan, you're not required to pay interest or pay payments while you're in school, but the interest is accumulating while you're in school. Okay? The interest is accumulating while you're in school. So you borrow $10,000. That's that initial amount. And 0.05 divided by 52 is not going to be pretty. So I'm just going to put plus 0.05 divided by 52, because you're not getting charged 5% every week. That's not what that means. It means those things are going to be expressed as an annual rate. Thank goodness it's not 5% every week. That would be craziness. And then it's 5 years, but times 52. So if you're dividing by 52 for the interest rate, you have to be multiplying by 52 to get the number of time periods. Now, I could pretty easily do 5 times 52 and get 260 in my head. And so then if you have made no payments because it's in your grace period, your balance at the end of the 5 years for that $10,000 you borrowed is now $12,838.71 before you even start paying. And many of those programs, like, people think it's a good thing. They're like, well, if you don't make a certain amount, you can put it on, you can have a delay, you can have more grace period, but the interest keeps growing. Okay, so the interest keeps growing. Or they may say, oh, well, we can base it on your income. You can just pay a smaller amount. But for some people, the amount that they're paying toward their student loans isn't even covering the interest. So they may have paid for 10 years and they still owe more than they borrowed, which is a very sad place to be in. Okay, so how would we figure out this $2,750 investment? How much is it going to be worth? It earns 3% compounded monthly. So 3% divided by 12, not 3% every single month. Now in this case, this says in 18 months. You do not need to multiply the 18 times 12. If it had said 18 years, yes.
1.5.
Or you could do 1.5 times 12. It'd just take you back to the 18. Do you see what I mean? So since it is compounded monthly and they gave us the date, the time in months, we don't have to, we could change it to 1.5. But then we'd have to multiply by 12, and we'd just be back to 18. But the percentage rate is a percentage rate, an annual rate. So we do have to divide that by 12. How much money?
$2,876.42.
42 cents? Is that what you got? Anybody else?
Yeah.
Did you say 76?
No. Wait, no, yeah, it's $2,876.42.
I'm not sure what I was doing. I had an extra 4 written down. I was like, this number is not reasonable. Okay, so here's some history intersection in our class. So you have all heard of Benjamin Franklin?
Yeah.
I hope. Okay. So he is credited with some wise saying like a penny saved is a penny earned, kind of things like that. Well, he was very generous, and when he died in 1790, he left a plan for Boston and Philadelphia. He gave both of them money, both of those cities money, but it had some agreements on it. some restrictions. They had to invest the money at an interest rate of 5% to be compounded yearly and then leave it untouched for 100 years. At the end of the 100 years, they were allowed to spend 3/4 of the money, 3/4 of the money on a city improvement project, and the rest would be reinvested for another 100 years at the same interest rate. So, and initially this was 1,000 pounds. At that time, that was about $5,000. 1,000 pounds is not $5,000 now, just so you know, but at that time. So, using the $5,000, figure out how much each city would have had at the end of the first century. So, the end of the first 100 years. It's just being estimated, compounded annually. So, you don't need to worry about dividing because the compounding is happening annually. So, you are using exponential, but it's compounded annually. It is. When I hear it pouring, then suddenly I'm like, is my sunroof up? And I'm like, it was drizzling when you came to work. Why would your sunroof be up? But it does. That's just like, yeah. So compounding annually, we don't have to worry about doing a division or a multiplication with our time. Pretty straightforward. So how much money did that give you?
$657,506.29.
Oh, hello. So, assuming that that is the correct amount, that's how much they had, they were allowed to spend 3/4 of it. So how much should be invested for the next 100 years? So if they can spend 3/4, that means they would still be reinvesting 1/4, which is 1/4. So if we take our answer from number 1 and divide it by 4, which means they should be investing $164 or $164,376.57. And then how much should they have at the end of the second 100 years? Because remember, they're supposed to invest this again for another 100 years at 5% again.
Oh boy.
$21,615,726.02.
So to get that, basically just this number that we had 5,000, this goes there. So you'd have the 164,376.57 times 1.05 to the 100th power. Just for laughs, I figured out what it would be if it was compounded daily. So if it was compounded daily instead, the first number, instead of being 657,000, it would have been 741,811. And the last number, this shows you some power of compounding. of course, over hundreds of years too. But the last number, if they compounded that daily, would have been 27,514,232.21.
Thanks for
Wonder
the
people do revolutions.
Just gotta wait 100 years.
I mean, that's like the rich just get richer, right?
So on the next page, this came up on one of our questions, and I just briefly told you. So this is just, I mean, there's math behind this, but the thing to know is this is a nice shortcut. That's approximately, if you want to know how long it takes for something to double. When I say double, like if you invested 1,000, when is it going to be worth 2,000? Okay? And a good estimate is to take the percentage rate, don't change it to a decimal, and you just do 70 divided by that. And it's a pretty good estimate. So let's see, find out exactly how much this would be using these numbers, and then let's see if it did about double. Again, it's not going to be exact, but it's going to give us an approximate. There are problems we could use exponential rules and logarithms, but because that is not part of the scope of this class, and also just that as far as a general doubling, particularly this was only compounded annually. If you did compound it daily, and there's also something called compounding continuously, then your rule of 70 is even closer to the actual. Because we know as it's compounded more frequently, it actually grows more. So it doesn't have to just be money. It could be something like population growth. So if Liberia has a population growth rate of 4.5, if I want to get an idea of how long it would take to double, I just do 70, divide it by 4.5. Bless you.